In this video, we'll take a little bit of time to discuss what's known as a Taylor polynomial. In prior videos, we developed the definition of a Taylor series and then used that definition to develop a Taylor series representation for e to the x. We'll actually get back to that particular Taylor series a little bit later on in this video to show how this new idea applies to it. But what we're defining on this screen is called a Taylor polynomial. The degree of that Taylor polynomial is going to be specified, and it's going to be for the function that the series was built off of, and it's going to be based at the same place where the series is based. So if you look right here, this is simply just the definition of a Taylor series without it extending to infinity. It's being stopped at n. And the reason why it's being stopped at n is because if you start with the index value of 0 and end with the index value of n, what you're going to have as the powers is you're going to have powers up till the nth power. One thing that you have to be careful with, and this is something that I've seen people confuse from time to time in the past, you have to be really clear on what it means by degree of a polynomial. If the polynomial is supposed to be of degree 2, if I was writing out the terms from the series in expanded form, I would need the 0 term, which you see here. I would need the first term, which you see here, because the power on the x here is a 1, and I would need this term that you see here, where the power is 2. Degree of polynomial is going to be the highest power on the variables within that polynomial. It's not going to be how many terms there are. Maybe that'll sync up from time to time, but in general, you need to make sure that you don't confuse this with partial sums. The partial sum of a series is how many terms you are listing. The Taylor polynomial is referencing the degree of a polynomial, meaning the highest power on the variable. So just make sure you draw that designation and act accordingly. So we'll actually show this idea in action. What we developed in a previous video is this relationship. The Taylor polynomial, the Maclaurin polynomial actually, so the Taylor polynomial for e to the x, which is based at 0, is this. What we would like to do here is we would like to find the Taylor polynomial of degree. We're not going to go degree n, we're going to go degree 4. So we want to find the Taylor polynomial of degree 4 for e to the x based at 0. We've already got the Taylor series, the Maclaurin series, since this one's based at 0 for e to the x. If we want a fourth degree polynomial, all we do is we start applying values of the index, right? Put 0 in place of these k's, and this is the value that you end up with. Put 1 in place of these k's, and you end up with 1x to the first. Put 2 in place of these k's, you end up with 1 over 2x to the second. We need to keep doing this until we get a fourth degree polynomial on our screen. So when I apply the index value of 3, 1 over 3 factorial, 3 times 2 times 1 gives me a coefficient of 1/6, and then x to the third power. And then I need one more value of the index, the k equals 4 index to go in order to produce that fourth degree term. So 4 factorial would be 4 times 3 times 2 times 1. The nice thing about doing factorials when you've done the prior one is this is 3 times 2 times 1. This is supposed to be 4 factorial, so I just have to multiply this answer by 4 to get my next factorial from that. This is it, because we're asked for a fourth degree polynomial. Now, if we were asked for a fifth degree polynomial, we'd have to go one term further. If we were asked for a 10th degree polynomial, we're actually going to look at that in about 30 seconds. We'd have to keep on extending this further until we have an x to the 10th on the page. So what we're going to talk about in the next few screens is the relationship between the function that the series was built from and this fourth degree polynomial that we're looking at right here. And we're actually going to start by looking at the relationship between e to the x. So I've got values of x here, so values of x 1 through 5. I've got values of e to the x, so when I put 1 in place of the x in that power, these are the decimal approximations I'd get. They're irrational. They're all e to power, so these are definitely all irrational. So they've all been rounded off to a certain extent. And then what I have here is you'll notice these 4 terms. That is our fourth degree polynomial from the previous screen. But then I did what I said you would need to do had you been asked to produce the 10th degree polynomial. I applied the index value of 5, 6, 7, 8, 9, and 10. So when I evaluate this huge polynomial, which is obviously lengthy, but when I evaluate it at these same x values that I'm evaluating e to the x at, Look at how close the relationship is between, look at that first line. This has been rounded off to what, 818 at the tail end of the decimal. You don't see any difference between e to the first power and this crazy looking polynomial evaluated at 1. So when I put 1 in place of the x's in this polynomial, what I end up with is a really accurate estimate for e to the first. If I put 2 in place of the x's in this polynomial here, I get 7.38, whatever, the rest of that stuff. When we look at what the value of e to the second is being rounded off to, we get the 7.38. We do see a 9 in that third spot. We see a little discrepancy between the two numbers that sit side by side within this row, but still a fairly reasonable estimate for e to the second power. Whenever we do the same thing with 3, e to the third, you see right here, this 10th degree polynomial evaluated with 3 in place of the x's. Again, there's more error than we saw from the previous line, but still a fairly reasonable estimate. We do the same thing at 4. We do start to see more of a gap develop here, right? The 54 is correct, but then we're at 0.59 here and we're at 0.44 here. So we're starting to see a gap develop between what the value of e to the x is and what the value of this 10th degree polynomial is. Couple reasons for that gap. We don't have the full Taylor series here. We've stopped it at 10. If I wanted to add on an 11th term, a 12th term, a 13th term, I would have a closer relationship between those polynomials evaluated at 4 and e to the fourth. The other thing that's happening here, this Taylor series that we've been working with, if I click back to the previous screen briefly, this is a series that's based at 0. Like you've dealt with regard to tangent line approximations, when you have a tangent line to a curve, the tangent line and the curve hit each other at the point of tangency. They're close together near the point of tangency, but then as you start to distance yourself from the point of tangency, you typically start to see a gap develop between the y value on the tangent line and the y value on the function. And you can use that same exact logic when you're dealing with Taylor polynomials. You can kind of think of these as like tangent line approximations on steroids almost. You have to take way more terms to make the approximation hold more closely than the relationship between a tangent line and a function does. But as we distance ourselves from where the Taylor polynomial is based, and again, this one, if I click back one more time, this one is based at 0. We see a close relationship at 1, a fairly close relationship at 2, but then we start to see more of a gap develop whenever we extend that out further. So what we'll try to check out next is we'll try to check out the graph of e to the x. So I just did this on Desmos. So e to the x, you can kind of see the horizontal asymptote of it extending out across the x-axis here. But you see the red graph here, but then this purple graph is basically right on top of the red graph. From, I guess you can see a little bit of a gap at -4, but then you don't really see any gap at all on the central portion of the graph here. You can't even see where the red graph of e to the x is. So what I graphed along with e to the x is I graphed the first degree Taylor polynomial. So I made reference to tangent lines a few seconds ago. This is actually the tangent line to e to the x at where the series is based. So a first degree Taylor polynomial for a function is actually a tangent line to the function at the spot where the series is based. So you see that tangent line graphed in blue here. This is, I guess, you maybe call it a tangent parabola. Our second degree Taylor polynomial is graphed in green. We see that the blue graph is close to the purple graph, which is on top of the red graph, near the point of tangency, near the place where the series is based. We start to see that gap develop that we talked about a few minutes ago. That's no surprise. We've seen that in the past. With the parabola, we see that the parabola sits on top of the purple graph, and especially up into the first quadrant here, it's much closer to the purple graph than the blue tangent line graph is. But then look at that purple graph. This purple graph, this is actually the 10th degree Taylor polynomial. This is the same polynomial that we had on this previous screen back here that we were looking at the table of values for. This purple graph is pretty much right on top of the graph of e to the x from the x value of, I don't know, like -3.75. I guess I could have extended this up into the first quadrant further to try to see how far that relationship extended outward across the x-axis. But conceptually, the point to make from this screen is that near where the series is based, you're going to see the function and the Taylor polynomial. They're pretty much right on top of each other. As you work outward from where that is based, you start to see that gap develop. But if you use more and more and more and more terms, you see much less discrepancy between the function, which again is the red graph, and the Taylor polynomial. And the highest order Taylor polynomial that we see here is the purple graph, the 10th degree Taylor polynomial, practically sits right on top of the red graph. This relationship could be extended outward across the entire interval of convergence of the series. The interval of convergence of this series to e to the x was negative infinity to infinity. Now you'd have to take many, 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 many terms, way more than the up to the index value of 10 that we have represented on the bottom line here with the purple graph. But you could expand this relationship outward across the entire interval of convergence of the series.